Thank you for the introduction. I'm going to present our work, a 1.6 milliwatt QVGA vision sensor with programmable dynamic background rejection and motion detection. Here is the outline of my presentation. Starting from the introduction, I will talk about the algorithm that implemented on chip, and then conclude with the sensor architecture and some experimental results. The work is part of Project FORENSOR, which is co-funded by FORENSOR 2020 framework. So basically, the aim of the project is to develop the low-power wireless autonomous sensors used to gathering evidence for the law enforcement agencies. And our main job here is to develop the low-power vision chip. So for this project, we would like to have a vision sensor with battery powered, which it means that we can leave the sensors at some isolated place working for few of weeks, few of months, with no infrastructures. But the current surveillance systems are usually really bulky. So most of the surveillance systems now is using some commercial cameras with high resolution. It's not energy efficient because most of the time it's just to force the processor continues to receiving images and processing images. But most of the time there's no event happened during the scenario. So our idea is to develop the always-on CMOS vision sensor, which consumes around a milliwatt, and has also an event-based operation on chip. So it means that when the vision chip sees some motions in the shine, it will generate alert to the processor, which consumes high power, and this processor will maybe wake the wireless transfer networks to transfer the data to the high-level servers. The wireless networks and the servers usually consume high power. So by event trigger, we can decrease a lot of the duty cycles and decrease the whole power consumption of the system. This is our algorithm implemented on each pixel. So the black one is the signal. Basically, we compare it with two thresholds, the upper threshold and the lower threshold. What it's doing that the two threshold is stored on the on-chip SRAM. So every time we compare it with two threshold, and the threshold is changing based on the signals. So it means that it can slowly learning about the background. When the signal is much higher than the threshold, it will generate alert. It means they're the hot event. And the gray zone there means a safety zone, so it means there's no event there. Here is the basic how it's done on the processor levels. We can turn opening speed and the closing speed, like showing here. When the signal is much higher, it will go faster. The threshold will goes faster. For example, if the signal is higher than the upper layer will increasing faster. When the signal is lower than the upper layer, the upper layer will start to approaching the speed, but approaching the signal, but with a much slower speed. Here is our emulator developed to simulate the result of the algorithm. You can see that the sensor output is a QVGA bitmap. The white point there, it means some event there. Thanks to the emulator, we can better design our vision chip. So basically, this vision chip can provide two different outputs. One is QVGA bitmap, and the other one is QVGA 8-bit gray image. So normally, we just send outside this bitmap to processor, which we can decrease the data bandwidth and decrease the power consumption. If the processor asks for high quality images, then we will provide this gray level image. This is our sensor architecture. So it is a QVGA A3, it's a 3D standard pixel, and with column level ADCs. Processor process each pixel, compare it with a threshold which is stored inside the SRAM every time every row when you are reading out the 8-bit data of each pixel. Here is just our ADC converter structures, column level ADC converter structures. The amplifier normally is working to amplify the signal, and it can also work as a comparator for the ADCs. Here is our photograph of our chip and some main parameters of the chip. So this chip consumes 1.6 milliwatts, continues working at 15 frames per second, and with a dynamic range of 53 dB. So basically, the upper one is a simulation of the MATLAB. So it's a 1 pixel simulation. So you can say when the pattern is periodically moving, it will first detect as an event because it's an event different from what it was before. And just after hundreds of frames, it will be absorbed as a background. Here is our developed demo, and we did also some outdoor tests. So you can see how it can clean and easily detect the moving boat and the cars without detecting the moving water ripples and the moving grass and trees. This is basically the advantage of our sensor, that it is robust and could be used outdoor. It's different from the some other motion detection cameras which are based on the frame difference. And based on frame difference, it's quite difficult to working outside with a harsh environment. So basically, we developed new QVGA sensors with background subtraction architecture on chip, and has a 1.6 milliwatt power consumption, and this could be suitable for battery operated applications. That's all. Thank you.